So thank you very much. And good morning, everyone. So as introduced, my name is Ady Stern, and I will talk to you about topological superconductors and Majorana fermions, and I'll explain what I mean by the title later on. Now, I see you all. I mean, people who sit in the lecture hall. If you have a question, make sure I notice. I'm not sure. So first, I'd like to say, maybe even before going to the outline, I'm grateful to the organizers for inviting me, in particular to Ayelet, who is a graduate of my own faculty, and we are always very proud of our graduates, and in particular in this case. And I'm sorry I'm not present there, but only speaking remotely. I'm not sure you are, so sorry for that, given that I spent the last 2 days sneezing and coughing. So I hope this will not be renewed during my talk. Anyway, my plan is, the outline is going to be, the talk is going to be divided into 2 parts. A short advertisement, which will take 1 minute, and the rest of the talk, which will take the rest of the time. So let me start with the short advertisement. So together with a few of my friends here at Weizmann, we prepared an online course called Topological Quantum Matter, in which we explain this list of subjects that you see now on the screen: the quantum Wall effect, topological superconductivity, topological insulators, superconductors, semi-metal, graphene, states of topological order, experimental tools, and so on and so forth. And you see it's a whole group of colleagues, mostly from here, but not only from here. And you can find the course on EDX and Campus IL, which are 2 online platforms, but also on YouTube if you search for Topological Quantum Matter Weizmann Online. There's an email address there in case you encounter a technical issue. So this was the advertisement. And now I'd like to get to business. So I'd like to, this slide basically gives the real outline of the talk. What I'd like to say is that one-dimensional topological superconductors are very exciting. And they're exciting because of reasons which I will explain in more detail in the next slide. But they're exciting because they're associated with localized Majorana zero modes, with topological protection, with non-abelian statistics, with topological quantum information processing. All are very, very, appealing concepts. So it's an exciting field, and I'm going to tell you why. I should also say, it's based on a straightforward theory. We're not doing any better answers. It's all a set of quadratic Hamiltonians, all very well tested in condensed matter physics for several decades. So it's based on a straightforward theory. But then, when we try to apply this straightforward theory to experiments with all this motivation of topological this and that, we find that they are pretty hard to realize. Majorana fermions, one-dimensional topological superconductors are much harder to realize, let alone to control and explore, than what you'd expect just from the simple theory. So I'd like to lead you from these 3 starting points to the conclusion that maybe we still did not find the right experimental setup to study one-dimensional topological superconductors, and I'd like to propose such a set. Okay, so this is the plan. So first, as I said, I'm going to argue that the one-dimensional topological superconductors are exciting. And they're exciting because they belong to a field of condensed matter physics called non-abelian states of matter. So now what are non-abelian states of matter? It's a simple concept that I can explain to you in a few minutes. When we talk about the non-abelian state of matter, we talk about a system where there is an energy gap between the ground state and the continuum of excitation. But not only that there's an energy gap, it turns out for a non-abelian state of matter, or for a state of matter to be non-abelian, there should be several degenerate ground state. And the degeneracy should be topologically protected, and I'll explain now what it is. But let me just check this. I don't know if you saw this blue circle there. Anyway, I will move. The degeneracy of the ground state should be topologically protected. What do I mean by that? What I mean is, this is how the Hamiltonian looks schematically. There's a subset of ground state which you see in the upper left block, and I put all the ground state energies to zero, just as a reference. Then it's a diagonalized Hamiltonian. I pretend that I diagonalize it, and I have a set of eigenvalues of zero, several degenerate ground states, and then some positive energies higher than zero, which I'll get from zero. And there are many of them. Now I take the system and I put in some perturbation. Doesn't matter which perturbation, as long as it's a weak one that does not cause a phase transition. What's going to happen to the Hamiltonian is this. The block that was non-zero before will stay non-zero. The three blocks that you see there will be non-zero. But the block of the ground states, the upper left block, despite the application of the perturbation, will stay zero. Meaning the perturbation will not be able to couple ground states to one another. This is the notion of topological protection. Now, if I rediagonalize the Hamiltonian again, with the perturbation, I will find the same number of ground states. And I will find only exponentially small separation or splitting of the ground states from one another due to the perturbation that I use. This is the topological protection of the ground state. No perturbation makes other than exponentially small numbers, which I'm going to pretend are zero. No perturbation opens splitting, opens up a split or splits up the degenerate ground state. Okay, now why is it good? So it's good for the following reason. You can ask, well, if I have ground states which are all degenerate to one another, how am I going to introduce the dynamics into the system? I'm putting my system in one ground state. Okay, it's degenerate with others, but it's orthogonal to them. So how can I introduce dynamics? How can I make the system move from one ground state to another? Well, the answer to this is that the system has, like all systems, has parameters. So, the wave function is a function of many electrons, but it has parameters. These capital R1 to Rn that you see there are parameters in the Hamiltonian, and we'll see which parameters can serve us for that. Now, as long as I don't change the parameters, there's no dynamics in the system. I put it in a ground state. The ground state is an eigenstate. I put the system in a ground state, it stays in the same ground state forever. But if I play with the parameters, in particular, if I take the parameters into a closed trajectory in parameter space, I will find that the system may change from one ground state to another, or from one ground state to a superposition of ground states, and that change will be, and then I introduce dynamics into the system. Now, the change, the transformation from the original ground state to the final ground state will be a unitary transformation, because I'm going to do this change of parameters adiabatically. So I'm not exciting the system. So it will be a unitary transformation, and that unitary transformation, it turns out, will be topological. It will depend only on the topology of the trajectory that I'm taking the parameters to, and not on the details. This is what makes this notion appealing for topological quantum information processing. It's the observation that I can apply unitary transformations to a quantum system, which are insensitive to noise and to fluctuations in the system. Okay, so this is why this idea of a non-abelian state of matter is exciting. Questions so far?
No.
No, okay. So I told you, and I hope I convinced you why it's an exciting field. Now the second item I posed before is that this notion of an non-abelian state of matter, I should say, only of that particular one that I'm going to discuss today, it's based on a straightforward view. So the idea of topological superconductivity, I'm going to tell you now, is really based on straightforward theory. And when I say straightforward theory, what I mean is a quadratic dimension. So let's look at that. You know, one-dimensional topological superconductors are superconductors. Superconductors, for theories like me, are systems you describe in terms of the Bourdieu-Worthe equation, the Bourdieu-Worthe Hamiltonian. Now, the Bourdieu-Worthe Hamiltonian you see there, it has normal terms H0 and minus H0, which are just non-superconducting terms which conserve the number of particles. And then it has this delta and delta dagger, which are terms which create Cooper pairs or annihilate. So altogether, it's a matrix. It's a quadratic Hamiltonian. You see there, it has either psi dagger psi, or psi dagger psi dagger, or psi dagger, or psi. Each one of those possibilities involves only two fermionic creation and annihilation operators. Okay, so it's a quadratic Hamiltonian. Now, we are not going to solve this at the moment. We're going to look at two very simple properties that the Bourdieu-Worthe Hamiltonian has. First, this matrix that you see there is even dimensional. The dimension, whatever it is even. Because look, it has H0 on the left, upper left, and minus H0 on the lower right. So whatever the dimensionality of H0 is, the dimensionality of the total Hamiltonian is twice this. So it's an even dimensional matrix. Right? This is easy to see. A little bit harder, but not much harder to see, is that the spectrum of the Bourdieu-Worthe Hamiltonian is symmetric around zero energy. Okay, so if I have a state at energy plus E, I'm going to have a state at energy minus E. And that comes out of a little bit of staring into this Hamiltonian. So what you see in the drawing on the right is a possible spectrum that has 6 states. 3 of them are above zero, and 3 of them are below zero, and they are symmetric around zero. Now, can I have a state at zero energy?
Can I ask a question?
Sure.
This is true, like quadratic Hamiltonian or this formulation, only for 1D system, or this is a very general for?
This is the superconductivity in general, okay. Not for one, yeah. It's this superconductivity. Okay. So now, if we're asking, can we have a state at zero energy? The answer is yes, but never alone. Because just from these two properties, even dimensionality and the symmetry of zero energy, you realize that if there is one state at zero energy, there must be another one. There must be an even number of states at zero energy. Otherwise, we're going to violate one of the two properties of even dimensionality or the symmetry with respect to zero energy. So if we have a zero energy state, there must be an even number of them. Now, this is very important. Because if I separate two zero energy, if I have two zero energy states, and I make them separate them, spatially, I put one here and the other one there, very far away from the first one, then the two are stable. Why are they stable? Because any local perturbation that I will apply around one of them cannot move it in energy. It can change its wave function, it can do many things, but it cannot change its energy. Because if we change its energy, the other one would stay alone, would stay a single one. And there cannot be a single zero energy state. There must be an even number of them. Right? So this is a very powerful observation, because it says that if we are able to separate two zero energy solutions of the Bourdieu-Worthe equation if we're able to separate them in space away from one another, they are topologically potent. Now, if that happens, it means that the ground state becomes degenerate. Because, you know, the solutions of the Bogorov-Degenn Hamiltonian are operators. And they are operators with which you act on states of the system. So if you have a zero energy operator, and here I call them gamma, each one of these zero energy states I call gamma. So if you take one of these gamma and operate with it on an eigenstate of the system, you get a different eigenstate, but you do not change the energy of the eigenstate. So you get a degenerate eigenstate. And that's what we're after, right? We're after degeneracy in the ground. So if we have this topologically stable zero mode coming out of these observations that we made about the Bogorov-Degenn equation, if we have that, we have ground state degeneracy. If we have ground state degeneracy, we are into the topological quantum computation.
We have one
Yes.
here.
Hello, Professor. Sorry for the interruption. I do want to ask that, just to clarify, the gamma is defined to be an operator that maps from one ground state to another ground state. Is that correct?
So you're asking what exactly is this gamma? It is an operator. Was this the question?
Yes, the gamma the operator that maps from one ground state to another ground state, given that the ground states are degenerate.
Exactly. You operate with this gamma on a ground state, you get a different ground state. How do you know that you get a different ground state? Because it commutes with the Hamiltonian. So it takes you from an eigenstate of one energy to another eigenstate of the same energy. How do you know that the two are orthogonal? Because gamma, it turns out, is a fermionic operator, and it changes the parity of the ground. So it will take you from a ground state with an even number of electrons to a ground state with an odd number of electrons. So yeah, it's an operator that takes you between grounds.
Thank you, Professor.
Okay. If we manage to have a system that has a superconducting system that has Majorana fermions or zero energy states, they are called Majorana fermions because they are described by the type of operators that Majorana invented in a different context. If we are able to find the zero energy states for the Bogorov-Degenn Hamiltonian that are localized away from one another, we're in the topological quantum computation business. So can we do that? There are several ideas for how to do that, and I'm going to briefly review first one and talk some more about the new ones. So the first one, well, not quite the first one, but the first one I'm going to cover here is the idea of topological superconductivity in nanowires. So what you see on the left is the initial experimental setup. It's a one-dimensional wire lying on a superconductor. The superconductor is a S-wave conventional superconductor. You put the wire on it. The wire is semiconducting, and we'll talk about it in a second. But anyway, it couples to the superconductor, and this proximity coupling will make the 1D wire into a topological superconductor. How it is going to happen? Well, the wire is 1D. And it should have, on top of kinetic energy for the electrons, it should have two more ingredients which are important. One, or maybe three which are important. One is the spin-orbit coupling, and what you see down there is the spectrum in the presence of spin-orbit coupling. Without spin-orbit coupling, we would have two parabolas lying on one another, one to spin up, one to spin down. Spin-orbit coupling moves them horizontally, one to the right and one to the left, and that's what we see. That's one ingredient. Second ingredient is the magnetic field. The magnetic field, what it does, it opens up a gap in the spectrum of the one-dimensional wire. It opens up a gap at momentum kx equals 0. X is the direction of the wire. Okay? And the third ingredient which we must have is the chemical potential. You see it in the Hamiltonian. So what happens is, in order to realize this topological superconductor, you need to put the chemical potential in the gap, excuse me, that you created by the application of the magnetic field. Okay, so an important ingredient in this is you need to fine-tune the gap. And those of you who actually doing this kind of thing, or experimenting, know that playing with the chemical potential of a semiconducting wire in the presence of a superconducting wire is a challenge, one of several that we have. Okay. Now this is an idea from about 12 years ago by two groups, my colleague Yuval Oreg and collaborators, and Roman Lucian collaborators, and basically, you need to take a one-dimensional wire, put it on a superconductor, put a magnetic field, and observe the Majorana at the two sides. That brings us to the third point, which I outlined before, which is despite the fact that the theory is straightforward, and I hope that I managed to convey this theory to you, tell me if I did. Despite the fact that the theory is also a quadratic Hamiltonian theory, it turns out the one-dimensional topological superconductors are quite hard to realize, and I'm going to say a few words about that now. Questions?
Not yet. It will come.
Okay. Following these two works that I mentioned, there was a pretty intensive research effort, and many results were obtained. You see here two examples. You see a couple more later, and basically people realized this wire, measure the timing density of states at the two ends of the wire. The conductance peak, so the density of states peak that is associated with Majorana fermion at one end of the wire, sometimes. At the other end, various types of wires were produced. One of the types that I explained before, another where you, instead of the wire lying on the superconductor, you actually wrap the superconductor around the wire. Various types of realizations. This is a very recent one from a couple of weeks ago by this 127 photos paper, where the wire is not really a wire, but confined. It's a 2D electron gas, so the electrons are confined to move in one dimension, and that's a very that's kind of an orthogonal realization centered around Princeton, I would say, where instead of looking at the wire, you arrange a chain of atoms, one close, you arrange atoms in chain and play with the superconductivity. With the superconductor, you put them on, and with coupling in the superconductor, and with a magnetic field, and again look at the density of states at the end. All those are encouraging results, but as you may know, there is no consensus on whether what is seen is indeed a zero energy state, zero energy Majorana state at the two ends of the wire. So there's no consensus, and there's a very heated, sometimes too heated argument about this. But what's more important, no one was able to do more than that, more than seeing this zero energy state. For example, to carry out motion of these zero energy states in in such a way that we create a topologically protected unitary transformation. Why? So, you know, you never know what the problem was until you overcome it. But there are really several problems which are built into these setups. One is you have a superconductivity and magnetic field, and those are two that can live together but not happily ever after, right? Magnetic field harms superconductivity, and in particular, the superconductors we're talking about are harmed by magnetic. Second, you have the same kind of uneasy coexistence of superconductivity and fine-tuning of the chemical potential by gating. And third, like always, we can always blame the disorder. The disorder in the system, and who knows what it does. So that is definitely a list of you know, reasonable suspects for what would be good to change to make this 1D topological superconductors easier to realize and work on. So, as I said, if the setup that we have, despite the simplicity of the theory, do not realize the system we want to realize in a very accessible way, maybe we should play with the setup and look for other possibilities. And that's what I'd like to do in the next 35 minutes. Mostly I'd like to introduce a new node. So far we had, we had superconductivity, we had a magnetic field, we had spin-orbit coupling, we had superconductivity. Now I'd like in particular to add the phase of the superconductor into the discussion. Okay, but before I do that, I'd like to sort of tell you what the rules of the game are. I'm a theory, so I'm going to make something that theorists do all the time and experimentalists never, which is I'm going to think about my one-dimensional superconducting system imposing periodic boundary conditions. Okay, that's the only thing I'm going to do. It's not going to be much more. So I'm going to think about the system with periodic boundary conditions. So you see on the screen now the two systems I'm going to talk about. The one-dimensional system is the channel between the two superconductors. The green things are superconductors. Each one of them has a different phase. So what we see here is a Josephson junction. Superconductor, the purple part is this is the color I see. I don't know what you guys see, but the purple is the lower part. Is a two-dimensional electronic system, semiconducting. And now there's a phase distance between the two superconductors. And you see on the right a variant on this, which I'm going to devote some time, where you have three superconductors, not just. Now, what are the rules of the game? We are going to impose periodic boundary conditions. This means that the momentum along the junction is a good quantum number. The junction will be very large because this is our one dimension. So it's going to be very long. The momentum is going to be well defined, going to be a good quantum number. Therefore, we can solve the problem of the general equation as a function of that number. And you see here two solutions, the energy versus K for one condition, for the other condition doesn't matter. But what's important is that you realize the energy versus K. Now, we're not going to have any zero energy Majorana states here because our system with periodic boundary conditions has no end, right? So we cannot have end more. And the zero energy state is here in the end. We're not going to have Majorana modes, but what we are going to look at are situations where Kx equals 0, the gap closes, a single gap closes, meaning two states, the topological of the general equation, the spectrum, as we said, is always symmetrically on 0. So two states are going to get to 0, one from above, one from below. And then I'm going to cross basically to 10 places. The one that was below zero will become above, and the one that was above will become below. So when that happens, this point, the point of the gap closing at kx equals 0 is going to be a transition point from trivial to topological or topological to trivial. Once we cross that point, if we now cut our periodic boundary condition, make the system into an open 1D, we will have to Majorana mode.
Sorry,
Okay, now.
Wait, what?
Here, this little figure that's difficult to see, these blue figures. You tune phi.
Let me wait a little. You probably know how to do that.
Sorry, I think you mean maybe this is the best, right? You see, yeah, this is the best function. The function of k.
Sorry, can you ask again?
Yeah, so he's asking about, I believe it's band factor.
In the center, that blue one.
Yeah, you see like the white and the blue. Like, you see the small picture? He's asking what is small picture is.
So okay. So again, what you see here is energy as a function of momentum. Okay? And this is zero energy, and you see it's symmetric on zero. And in this particular case, chosen not by coincidence, you see a gap closure at kx equals 0. So this point is very
phi here. What do you tune?
This one is not.
No, I'm saying that from left to right, what do you tune? You tune phi to go to the phase transition?
Okay. What I tune from here to here, it's phi, yes. It's fine, but also, okay, I'm going to tell you what the system is. It's this system, and this system has two parameters, the phase difference and the magnetic field, a parallel magnetic field going along the junction. I'm going to introduce the system in detail in 2 minutes, but going from the left plot to the right plot, I'm changing the phase difference and the magnetic.
Yes, thank you.
Okay? So the rule of the game is we need to look for a single gap closure. Now, one thing should be clear from that. Since I insist on a single gap closing, there cannot be spin symmetry. Because if I say spin symmetry, then each one of these lines will be W degenerate. And the only kind of gap closing that I'm going to have will be a double gap closing. And I need a single one. So spin symmetry must be broken. And that can be done either with a magnetic field or with a spin-orbit coupling or with both. If I look here, the energy as a function of some parameter at kx equals 0, I should have a single gap closing, not two of them. And if I have two, I should look for a way to separate them from one another. I should take this to go Italian's understanding of one dimension topological superconductor. So now let's talk about the system I'd like to talk about. It's the same drawing I showed before. So we have a superconductor, superconductor system. There's a phase difference across between the two superconductors, which is phi. There's a magnetic field in the x direction. And I'm not going to go into too many details, in particular that I see how time moves. But what I'm going to tell you, first of all, relative to the wire realization that I talked to you about before, there are new nodes. There's a phase difference which you can tune, and there's a Josephson current. You can push a current between the two superconductors, and you can also put another magnetic field perpendicular and have a flux effect, not a Zeeman. So given all these new possibilities, what are we going to find? And I'll tell you how we find it. We're going to find several findings. First, we're going to see that if the phase difference is phi, close to phi, there will basically be a topological phase with very little magnetic field. Now, as we said, a magnetic field is double field because magnetic fields and superconductors don't coexist very well. So reducing the magnetic field is of value. We'll see later another scheme that eliminates it completely. And the second thing I'd like to tell you is that this system, in some sense, can tune itself into topological state rather than ask you to tune it. So as we said, there are two parameters in this system. There's a phase difference and a magnetic field. And what you see in the plot is a two-dimensional parameter plane, phi in the y-axis, magnetic field in the x-axis, and you see the blue, or kind of pale blue part of the diagram is the topological part. So you see when the phase difference is phi, in principle, there's a cusp of the topological part that goes all the way to zero magnetic field. Now, this is under very idealistic conditions. The more realistic conditions, as you can see by the dashed line, take you away from zero magnetic field. But clearly, when the phase difference is close to phi, it's easier to make the system topological. Now, in the case of the wire that I showed before, there was also a somewhat similar phase diagram where on the x-axis you have the same Weizmann coupling that you have on the left, but on the y-axis you have the chemical potential. Now here the new feature of the first conductor is you hardly need to tune the chemical potential, which, as we said, is another type of trouble you'll be happy to get rid of. So there's only a weak dependence on the chemical potential. Now there are conditions which I'm not getting into details of, but some of them will come up later. Now that's one thing. The other thing, as I said, the system can tune itself into a topological phase in the following sense. In principle, we have a two-parameter phase space, magnetic field and phase difference. In fact, you can play the following game. You can change the magnetic field and not control the phase difference at all. Just let the system find by itself the phase difference in which its energy is minimized. If you do that, you find that the whole region of magnetic fields, which you see here in the red line, a whole region of magnetic fields where the system and the ground state of the system is in the topological state. So as you change the magnetic field, the system will go to a first order phase condition into a topological state. Now, it turns out this comes together with a minimum in the critical current, which, so your speaker from yesterday, Amir Kobi, carried out an experiment of a similar type and looked at the critical current as a function of the Weizmann field, which is what was plotted on the left lower plot, and you see that the critical current goes down with further field, but then recovers and goes up and then down again and so on. And what you see here, I'm erasing the data that's relevant, what you see is the critical current as a function of the parallel field, and you see that it has such behavior. So I don't know if it's the same, this is really the origin, but it's suggesting that what this is what this system is supposed to show. Now, how do we see that in this bit of detail? Our two-dimensional system is 2D with a spin-orbit coupling, alpha spin-orbit coupling, and a parallel magnetic field. In the absence of the parallel magnetic field, due to the alpha spin-orbit coupling, the spectrum has two Fermi surfaces with a different radii. But you see a big Fermi surface and a small Fermi surface, and the difference between them comes out of the spin orbital field. If you put in a parallel field, what happens is that they move relative to one another. So you saw that, I'll show it again. They move relative to one another. Here we think about the Zeeman field as weak, so the plot is kind of exaggerated, but that's what happens. And now on top of that, we put the superconductors with the phase difference. Now, according to the rules of the game that I told you, what we need to do is we need to solve the Bogoliubov-Dejean equations. For kx equals 0, where kx is the momentum along the junction, kx equals 0, and for this particular setup. So you see, it becomes a zero-dimensional system. It basically becomes the problem. Once I set kx equals 0, I basically have the problem. Sorry, I basically have the problem of a particle in a box, where the box, instead of having normal walls, has superconducting walls. So you need to do the Bogoliubov-Dejean analysis. The reflection going here and there at kx equals 0, and look for single gap closing that we talked about. Okay? Now, you know, it's a particle in a box. Okay, it's superconducting, but you know, the walls are superconducting, but the particle in a box always has the same method of solving, and this is the Bose-Sommerfeld condition. Right? You sum up the phase that you accumulate as you go back and forth, you sum it up correctly, you say that it's 2 pi times an integer, and you get the quantization condition for the energy that you're looking at. Right? So I'm going to look at the Bose-Sommerfeld equation here, but before that, I thought that I heard someone who was interested in asking something.
No.
No?
No.
Okay, so I'll use this excuse to.
Oh, wait. No, we have one.
Good.
So when you were talking about the magnetic field, do you mean DC magnetic field, like when it's constant in time, and Josephson current is the DC current?
Yeah, everything is DC. Magnetic field is DC, doesn't change in time, and the flux does not change. The phase difference does not change in time. Yes.
Okay, and if B field is changing in time, so the Cooper pair splitting has to form vortices, and the Josephson current must be the vortex line connecting each other to the Josephson.
You're asking if the magnetic field changes in time?
Yeah, I'm just trying to test my understanding because it's
So the magnetic field here, the parallel magnetic field plays only a Zeeman role because it's parallel to the two there. Now you can ask whether it is realistic, and that's a different question, good question. But and I'll come to it. But to start with, in the Hamiltonian that I wrote, it's a DC magnetic field. Now, and it's Zeeman. It's only Zeeman, you see.
And
Now, if I make it time dependent, I basically am going to make this motion go up and down, up and down. That's not going to well. What it's going to do is it's going to take me this 2-parameter plane. You know, phase diagram that I showed before, it will take me in and out of the topological phase that one thing may do. But do I answer your question, or?
you just give me more thoughts, so yeah, I'll think more about this. And the second question, when you said you treat everything as mean field theory, so essentially you say that Cooper pair is a boson, and you kind of write a Hamiltonian for bosonic particles. I was wondering, did people try to do the same but using Dirac equation when they actually treat the Cooper pair as individual particle connected, to, like mediated by a phonon, for example?
So Yeah, the answer is yes. For the question, if people buy, the answer is yes. Now, what comes out of this is this. So, the main difference between treating superconductivity by mean field and treating it with an Hamiltonian, that includes interaction with phonons and so on, is the issue of charge conservation. So in mean field, we don't conserve charge, and therefore the phase is well defined. If you think about full treatment, you conserve charge, therefore the phase is not well defined. Now we should ask first what is the right thing to do. So in these cases where the superconductivity always comes out of proximity coupling to a big superconductor, then we always justify doing mean field. You can ask what happens if we're thinking about a system where superconductivity is intrinsic. And that's a good question. If it's a one-dimensional system where superconductivity is intrinsic, it turns out the Majorana modes are not necessarily topologically protected. They may be too fragile in some sense. By that, what I mean is the wave function does not decay exponentially into the 1D system, and therefore they see one another, at least at the power law level. Okay?
Yeah, okay, thank you. And the last question I have, no little question.
Don't promise you.
So the last question is basically, were these one-dimensional superconductors realized experimentally, or is it still in progress?
Oh, I'm going to talk about.
Okay, because the reason why I'm asking, I remember from my course on like lattice quantum field theories that this kind of structures, 5 to the 4 potentials, usually described by the gauge theories, especially when you couple with external magnetic or electric fields or a combination of them. And I just remember there were like theorems essentially saying that the gauge field starts only with dimension 2, so which basically tells you that in dimension 1 you cannot realize topologically stable system. So I was wondering if this is the reason why you kind of try to tune the magnetic field so you can get this stable configuration of the topological charge.
So what was the reason you said that you cannot do it in 1D?
So that's basically an extension to Wagner theorem, which says that as you go to one dimension, your superconductivity becomes unstable under certain conditions.
Yeah. So this is why we always proximity couple to a 3D superconductor.
Yeah.
So basically, the wire I showed you was one-dimensional, but the superconductor that was wrapping it was by far three-dimensional, thousands of Kelvin. So now you can ask how will this basically disappear if the superconductor becomes one-dimensional by itself. And that's what I was saying. It's pretty hard to keep the Majorana states exponentially decaying. And indeed, the fate becomes defined and you lose much of it. But here, experimentally, the superconductor is always three-dimensional.
Okay, yeah, thank you so much.
Okay. More questions? So what we said is we need to solve this zero-dimensional, particularly in the box problem, and I suggested the Bose-Sommerfeld as a way to do that. Now in the Bose-Sommerfeld procedure, you just look what phases do the particles accumulate as they go back and forth between the walls. And here there are 4 types of phases. 2 phases are phases that are accumulated while you move from the right wall to the left wall. And those 2 phases are the kinetic phase, the momentum integrated over position, which is basically the energy times the width divided by the velocity, and the Weizmann phase. So those are the third and the fourth terms in this equation. The first 2 terms are phases you accumulate as you are being reflected from the wall. And it turns out one of them is the phase phase difference between the two superconductors, and the other one it comes out of the basically the boundary conditions on the wave function. Altogether, if you so you now are supposed to solve this equation for En, the eigenvalue, the nth eigenvalue of the potential equation, and ask when it is going to be 0. So the solution becomes easier if it's a narrow, W is small, and what you find is that the energy of state is delta, the superconducting gap on the two sides, multiplied by cosine of half the phase difference plus or minus half of the Zeeman phase that we accumulate as you go back and forth. Now, that's exactly what we need, because what we need, let's draw it. So let's first draw this without Zeeman field at all. So without Zeeman field, we are in our parameter plane, we are on this line, right? Because this line is the magnetic field, Zeeman field, and this line is the phase difference. So now we are on this line, and you see the energy is delta cosine phi over 2 without this plus minus. So when phi equals phi, and cosine phi over 2 is 0, when phi equals phi, we have a gap closing, but it's a double gap closing. It's not a single one, because we were not able, because we don't have the plus minus there, because it's plus minus 0. So now we need to turn on a magnetic field, namely move in this direction, turn on a magnetic field and move in this direction, and then we separate the two gap closing points and make it one of them a single gap closing point. And then we have a region in which we have a topological phase. So before, we had a transition that took us from trivial phase to trivial phase. After, we have trivial, topological, trivial. And all this analysis, basically the only place where the chemical potential occurs was in the Fermi velocity, which depends pretty weakly on the chemical potential. So there is no need for a fine-tuning of the chemical potential. Is this clear? Okay, now you can solve numerically the same system without, not in periodic boundary conditions. You can basically cut the periodic boundary condition, make the system into a single wire, and look at the ends of the wire and see whether you get Majorana states or not. And you see this is the damping density of states at the end at 0 energy, and you see this 0 mode here, which you don't see in the bulk. You see it only in the end, and this is the Majorana end mode that we are. Now, can this be seen experimentally? So there are several experiments done by Tony Marcus group in Copenhagen. That's the first version, and what you see here is the 0 energy. This is the spectrum. This is energy, and this is the phase difference, and you see these 0 energy peaks occurring, and here you see a second generation where again 0 energy peaks occurring. I should say the peaks are not huge. The results are not yet, unquestionable, but at least you see something that seems to be in the right direction. There are experiments also by Amir's group.
What the y-axis in the previous slide? To the y-axis.
The y-axis in all these plots was the energy. You basically measure the spectrum as a function of energy, the y-axis. It's a color plot, right? So the color is how much is what the damping density of states at the ends of the wire. Y-axis is the energy, so you are looking for a peak at 0 energy, and the x-axis is some parameter that you have, either the parallel field or the phase field. Okay. So there are also encouraging results from Amir's group. also measurements of the critical current, not without measuring the tunnel intensity of states. We see the non-monotonic behavior that I briefly discussed. All those are encouraging, but still leave much to be desired. Because the peaks are not very large. We cannot control, we cannot move those peaks as we want. We still suffer from the problem. I should have showed it. If you look here at the magnetic field in the x direction, which you would like to be 0 when the phase difference is pi, you see that it's still a quarter of a Tesla. That's about 1/4 of what it is in earlier realizations. So we are in the right direction, but we'd like to get rid of the magnetic field completely. And that's what the next realization which I want to show you deals with. So what I want to show in the rest of the time I have, I'll be careful not to ask how much time I have. I'd like to show you a setup where we basically need no magnetic field at all.
By the way, you have 5 minutes.
How much?
5 minutes.
But I had many
Yeah.
At least some liberal look at the one. Okay, the setup I'm going to tell you about now, and that's from a very recent paper with Weizmann Institute from St. Corridor. The setup I'm going to tell you about is this. It's superconductor, normal, superconductor, normal, superconductor. So we're going to have 2 phase differences, and we're not going to have any magnetic field at all. So the rules of the game. We need to have single gap closing, and for that we need to break spin symmetry. So we already talked about ways to do that. We talked about this Weizmann way. I didn't say anything about the other 2 ways, but there are also other ways to separate the spin transitions or to break spin symmetry, either by using 2D topological insulators or by spin polarizing the electrons. But in any case, what I want to talk about now is how to separate the transitions of the 2 spin branches by having the 2 spin branches having different velocities. So let's look at that. First let me remind you what we saw about the S and S problem. What we saw was that whenever the phase difference was pi, which in the notation I have here is theta equals plus or minus pi over 2, whenever the phase difference was pi, even without a magnetic field, we had a gap closing point. The gap closing. Okay. Now, if there's a spin symmetry, this gap closing would be doubly degenerate, and that's what we'd like to avoid. So what we're going to do is now we're going to add a 3rd superconductor, and that's the superconductor at the center. It will have its own phase. This was theta, this was minus theta, and the one at the center will have pi. Okay, and now we are going to ask what will it do? What will the addition of that superconductor do? And I'm going to think about it. I'm going to think about it as a function of the width of that superconductor. So if the 3rd superconductor is infinitely thin, then it doesn't do anything, right? And then we can forget about it. In contrast, if it's very wide, then it basically breaks the junction into 2 different junctions. So if it's very thin, what we said before is going to hold. And if there's a phase difference of pi here, we're going to get the gap closing. In contrast, if it's very broad, we need a phase difference of pi between these two, or a phase difference of pi between these two, because we now have two different junctions which are separate from one another. So it all depends on how wide the superconductor is. But wide compared to what? The only other length scale to compare it to is the coherence length of the superconductor, is how fast the states decay into the superconductor. So what we need is to compare the width of the superconductor to psi. And now the key point is, let's look for a situation in which psi has different values for one spin direction and for the other spin direction. And to have that, psi is a Planck's constant and the Fermi velocity divided by the superconducting gap. Now, Planck's constant is not going to change according to spin direction, and that is not going to, the superconducting gap also. But the Fermi velocity for two spin branches may be different. So what we want is to find a material and a parameter and a width in which for one spin branch the W will be much larger, the width of this superconductor will be much larger than the coherence length, and for the other spin direction it will be much smaller. Then we will have the two superconducting or the two gap closing conditions occurring in different values of the phase. And the only thing we have are phases, no magnetic. Okay? Now, so what we need is a spin-dependent Fermi velocity. Now, if that happens, we can solve the condition for having zero energy state as a function of theta, phi, and the ratio of this width W to the coherence length. We can solve this and then draw it on the two-parameter plane, which is in this case now is phi on one axis and theta on the other axis. Only two phase difference. No chemical potential, no magnetic field. And you can on these two dimensional parameter plane, you see that the topological region and how big it is depends on how different the Fermi velocities for one spin direction and for the other spin direction are. Okay? Now, there's a practical advantage to this, which is you can make basically the normal part as narrow as you want, and that increases the energy gap. But that's a side advantage. I should also say the solution that will give you a topological state. A necessary condition for such a solution to exist is that phi, theta, and minus theta, the three phases on the three superconductors, create a triangle that includes the origin. So in some sense, you need those three superconductors to form a vortex. Now, can we find the materials with different Fermi velocities? There are two ways to do that. One is you go to some material books or material databases or friends who know material science, and that's what is known in the literature about Fermi velocities for the two spin directions. And you look at the Fermi structure of many of the timely materials, mercury, telluride, various CMPs, molybdenum, SSCP, WSSCP, all those SPP2. All those will have Fermi velocities for two spin directions which are different from one another. So, and I think, in fact, that it very well may be that the future is in this type of material. It is in using PMDs as the normal path which that's one way of doing that, just looking at known materials and asking, can we find the material where the Fermi velocities are different for the two spin direction? Another way of doing that is to think theoretically what properties should material have to have unequal Fermi velocity. So that when you start thinking about that, it brings you to the question of what I call presumption of innocence or presumption of guilt. Should we expect the two, if I have a system where I have no spin symmetry, should I expect the Fermi velocities of the two spin vectors to be the same or not? And we sometimes think about them as if they're going to be the same, because in the Rashba model, where the effect of spin-orbit coupling is only to shift the two parabolas away from one another rigidly, then you have the same Fermi velocities for this branch, and for this branch. Now, that's for the Rashba model. But the Rashba model is an approximation, not more than that. And there's nothing in general. When you analyze the role of spin-orbit coupling in general, there's no way then to expect the Fermi velocity to be the same. And you can show that in 1D, the Fermi velocities will be the same if you take into account only nearest neighbor hopping. But once you include also next nearest neighbor hopping, it's not the Fermi velocities are not the same. And I don't have time to get into that, but if you think about, let's say, a TMD material on which you put two superconductors, there is no reason to expect the Fermi velocities in the relevant direction to be the same. So I think, how long you want me to go on?
-6.
-6. So, okay, so I'll skip this. I'll just tell you, well, there are also two other ways to make the Fermi velocities unequal. One is by playing with the parameters of the heterostructure, and the other is by having a periodic structure in the x direction. If you're an experimentalist, and this is of interest to you, there's much more to be said about this, but I won't say. The last thing I want to say is about disorder. You remember we had a list of troubles, a list of suspects, why we find the realization of one-dimensional topological superconductors so hard to construct. And the last one of them was the effect of disorder. And what I don't have time to get into this in detail. This is work with Abel Chaim with now in Caltech on the way to Hebrew University. I'll just give you the numerical observation and not get into its explanation. But so what you see here is this. This is the localization length of the Majorana end state as a function of disorder. Now, of course, the more localized Majorana end states are, the better off we are. Because then, if you put them on the two ends of a one-dimensional system, you want them to be as localized as you can, because then you can make the system not that large. So now you see what the disorder does to the localization length of the Majorana close to the end. What you see that weak disorder makes the localization length go smaller, which is good, because it makes the state more localized. If you get carried away and make the disorder stronger and stronger, at some point that magic doesn't happen anymore. But for a while, weak disorder can in fact work for you if you know how to tune it right. So I won't get into the details. I'll just summarize. And I'll summarize by saying, we clearly are not at the bottom line, at the end point of the search for Majorana fermions that can be manipulated and can be made to show topological protection and topological quantum information process. We are not there, we are far from. Why? Some of the difficulties are probably associated with superconductivity and magnetic field and gating all not being compatible to one another, and with disorder. We believe that we have some solutions, and which I presented to you. Either replacing the magnetic field by tuning of phasors can first of all take out the magnetic field, and second, alleviate the need to fine-tune the chemical potential. And even though I did not tell you about it in detail, we believe even the effects of disorder may be weak. So I'll stop here. Apologies for being too long. I'll try to give you 12 minutes back on the webinar. Perfect. Thank you very much.
Thank you very much, Dr. Stern. Could you please go to the page on about the toy model where you show the Hamiltonian?
So there were quite a few Hamiltonians here. Tell me
Yeah,
which one.
your model, yeah.
This?
Yeah, this is good, yeah. So in this case, you have this K-square with 2n. But my first question is, does it matter whether you have n positive or negative? So whether your 2 that is whole likely electron like, does that matter whether you will have Majorana or not?
No, whether it's electron like or like.
Yes.
Not very good. No, it's not very good.
Right. Okay.
By the way, not really because I can go to the thing better. So it doesn't make a difference whether it's electrons or.
I see. And so what about if you replace this parabolic dispersion by a linear dispersion?
By linear dispersion?
Yeah, like a graph.
Yeah, as long so if you have two Fermi surfaces of this type, then you find what do I mean by this type? Well, the spin has this pi rotation as you go as a 2-pi rotation where you go around the Fermi, then you find. And that happens also for the arc cones. Even more than that, if you think about using normal systems with Ising spin-orbit coupling, then the last setup that I showed, the S and S and S, will work also with Ising spin-orbit coupling. In which case you have a Dirac dispersion plus spin-orbit, the spin points up in one Fermi surface and down in the other Fermi surface. That would not work in the case where you need to put a parallel field, but would work in the case where you don't have, where you use the two-phase systems.
Thank you. And one more question with that, since you talked about the effect of disorder and saying that weak disorder is okay, it's actually good for having localized Majorana zero mode. I still want to ask you to compare between the situation of disorder in this setup using SNS junction versus using nanowires. Do you think this SNS junction can be made cleaner than nanowires?
Yeah, I think if you look at the effect of disorder on the nanowires, it's always negative. One maybe way to think about it is this. In a nanowire, you rely on fine-tuning the chemical potential. Now think about disorder as a spatial variation of the chemical potential of the bottom of the band. Let's say disorder is just a potential that changes slowly. Then in a nanowire, this slow variation will take you in and out of the topological phase. Every time you're taken in or out of the topological phase, there's a Majorana zero mode. So instead of having one Majorana zero mode on one end, another on the other end, you're going to have also many along the way. And they will couple to one another and eventually make the end one, in which you're interested, couple to one another, and the Gauss degeneracy will be split. In contrast, in the cases where you don't care where the chemical potential is, a chemical potential disorder will have a much weaker effect. Now, a phase disorder will have a bigger effect, but phase disorder is not something you encounter on daily life. In daily life, samples have a fluctuation of the potential. Okay, so this is why I think that the Josephson junction realizations will be less sensitive to disorder.
Thank you very much. Thank you.
Hi, Ady. This is Jiao Lian. May I ask a question about the Majorana? So the Majorana zero mode is on the boundary of the topological phase, right? So if you want to move the Majorana zero mode, what's the best proposal here?
If you want to move them, how do you move them? Thank you. I didn't pay you about this question.
Yeah. You need to control.
So the way to do that, I won't get into a new talk on this, but the way to do that is using two new knobs. One is a perpendicular magnetic field. Now, when you put in a perpendicular magnetic field, the phase varies along the junction, so you are not on a point in the parameter plane, but you are on a line. And then you can be, the end may be topological, but then there would be another two conditions inside the wire, the 1D system. That's one knob. Another knob is pushing a Josephson current. If you put the Josephson current in this direction, basically you shift this line up and down. So you shift what's the phase at the beginning and what's the phase at the end. So by playing with these two, you can move around the Majorana, and in fact, we came up with a scheme that here you see you have three Josephson junctions, and by playing with the Josephson currents between or across those three junctions, we have a scheme for braiding of Majorana. It's not exactly something that will happen next week, but it's a theoretical level.
Thank you.
We have time for another question from the webinar. Yeah, this attendee is asking, in Josephson junctions where the phase difference is different from 0 or pi, time reversal symmetry is broken. Can you comment on the differences or advantages of breaking time reversal symmetry via an external magnetic field versus via phase differences? And would disorder be equally problematic in both cases?
Okay, so if I got it right, the question is comparing the SNS to the SNSNS in terms of what the effect of disorder, right? This study, which I basically I showed you only the numerics, was on the SNS, and we did not get carried out for the SNSNS. I think that in general, situations where we play only with phase differences and not with chemical potential, or where we do not depend on the chemical potential being fine-tuned, I think they'll be less sensitive to disorder. Now, as to the breaking of time reversal by phase differences or by as compared to by magnetic field. The point is the effect of phase differences is very confined. You know, they affect only the Josephson coupling. While you put in a parallel magnetic field, then you introduce both distance between the superconductor and the two-day. So you affect the proximity coupling. The two-day, in fact, has a width of itself. So you put a parallel field instead. There's also an orbital effect. So I think in some sense the phase-only configuration or phase-only setup is more gentle. It's less violent to the entire structure. That's why I hope it will be more successful. I should say, by the way, that this last this SNSNS junction is a very recent work, and there's no experiment being done at the moment. And I don't know. I assume just naively that half of you are experimental. So I hope you listen.
We do our best.
Okay, okay, next question.
Hey, Professor Ady. So, I mean, so there was a problem that I was working on some time back. It was essentially about finding experimental signatures for Majorana Kramer sphere. So, I mean, I just wanted to know your insight, like what does go wrong with a setup in which, I mean, so we kind of said that we'll have a quantum dot, and then we'll couple it to a time reversal invariant topological superconductor, which can be probably realized, and then we with the flow of the coupling constant of the Kramer sphere with the dot, we study the flow of the Hamiltonian, and we did saw that the fixed point changed from, I mean, it did depart from the Kondo fixed point. Like we studied the spin susceptibility stuff. So the Kondo, I mean, the Kondo should quench the magnetic moment, but we did saw that it departed from that. So I quite didn't understand the practically why it usually doesn't work with such systems. I mean, yeah, if you could put some insights on this.
Why the original setup?
Yeah.
Why you know, I wouldn't say it doesn't work. What I would say, you know, clearly we haven't yet found the solution for realizing, you know, the analog of the silicon transistor for realizing a 1D topological superconductor. So I think we should search broadly. I'm not sure the last word was said about you know, the kind of forward-looking setup. Maybe adding quantum dots, and maybe you know, cleaning the material, and maybe making it not edged wire, but or not crystalline gone wire, but crystallographically gone wire, but this type of gating out today to a wire. Maybe that will help. I don't know, but I think we need, definitely me as a theorist, I need to search for other realizations, which maybe will have an advantage over the original.
Okay, I see. Thank you so much.
Okay, so let's thank the speaker again. Thank you so much.
Thank you very much, and I'll see you soon.
Yes. Thank you.
Thanks. Bye.
Bye.